Wingwag. I'm your host, Jack O'Lynn. I'm an instrument-rated pilot and the owner of an aviation company and flight school here in Central Florida.
This podcast is for informational purposes only and is not guaranteed to be accurate or complete. While we research each topic, we are humans and occasionally make mistakes. For the most up-to-date information on regulations, check out the official Federal Aviation Regulations, also known as the FARs, or consult an aviation attorney. Lastly, the opinions expressed on this podcast are the guest's opinions and are not necessarily the opinions of the host or podcast. Welcome to this week's episode of The Wingwag. If you remember, last week we did our first episode on navigation, talking about dead reckoning, not deduced reckoning, Hunter.
It's short for deduced reckoning. Okay. Mm-hmm.
And in this episode, we're going to talk about the next logical step, which is celestial navigation. It's a method of navigation that's very old. It goes back to basically the beginning of navigation. And I brought my brother Hunter here because he's an amateur astronomer.
An expert in navigation, I would say. So.
And an expert in navigation. Mm-hmm. So one thing I want to say real quick is you probably haven't listened to the other episode because it hasn't been released yet.
Nope.
But in the Dead Reckoning episode, I talked about how when people say they're using Dead Reckoning, they're usually using a version of Dead Reckoning where you Dead Reckon for a short amount of time, and then you update your location based on a true value.
So you're Dead Reckoning from your last known location.
Exactly.
It's like daily.
Right.
Like
so when you finish your PPL, you'll see they make you do this in the training where you basically Dead Reckon to a waypoint, and then you notice, oh, okay, I'm off a little bit, go to the waypoint, and then reset.
Yeah.
So that's one way to update it, is just using a landmark. That's probably the most common way you do it when you're just flying VFR. You could also do it with a GPS, and that's what like an airliner's inertial reference unit does. Or what they used to do back then when they were sailing across the ocean before they had GPS, and there's no landmarks obviously in the ocean, they would use celestial navigation. So they would Dead Reckon for a couple of hours, take some readings using various ways we'll talk about, use that to update their position, and continue on like that. And this is an aviation podcast, so there is another aspect. Do I have the book with me? Yes.
What?
The Big Hop.
Oh.
Great book. It's about the first people to cross the Atlantic in an airplane.
Not Charles Lindbergh?
Not Charles Lindbergh.
Interesting.
Charles Lindbergh, I'm trying to remember what his record was. I think it was first to cross the Atlantic solo.
I thought his wife was his navigator typically. Or maybe he did do a solo flight. I remember reading that like he really wasn't much of a navigator himself.
You're right. He was the first to fly New York to Paris.
Okay.
These people flew from was it Nova Scotia? Newfoundland. St. John's, Newfoundland to Newfoundland. To Ireland. The method of navigation they used, or at least what one of the planes used, was basically this. Dead Reckoning, and then every now and then they'd climb up above the clouds, get a reading to update the position.
I wonder how much they were over, or how much were they out of sight of, if the weather was good, how much were they outside of land for?
The weather was bad.
Okay.
Doesn't matter. I won't spoil the book, but there were a lot of difficulties, and weather was one of them. So like some of the teams were like, it seemed to be in clouds for like most of the time.
Got it. So in your Dead Reckoning podcast, you went over like the instrument that planes have that like take into account the airplane speed and wind direction stuff, and kind of like
they call it either the inertial reference unit or the inertial navigation system.
Have you flown a plane with that?
No.
Okay, that's only in like.
I don't know. So airliners definitely have it. Private jets have it.
Still,
yeah. Cool. Because I don't know why, but at least at work, a lot of other avionics will only take readings from the IRU. I don't know exactly what the reason for that is, but then, like I said, the IRU will update itself via the GPS pretty frequently. Sometimes down to every couple of seconds, it'll pull a new reading.
So pilots aren't actually like handwriting last known positions and.
No.
Okay.
The pilots, like they know that this thing is here, but they are not like actively celestial, or they're not actively Dead Reckoning any more than a normal pilot does. Because like when you think about Dead Reckoning, is kind of the default navigation that the human brain does when you're just walking around.
Yeah, when we fly, I basically dead reckon.
Yeah.
If I don't like, I'm not familiar with the terrain. I'm just guessing.
Or when we're hiking, a lot of times we're just talking, and every now and then, like, wait a second,
Yeah.
where are we? Yeah,
When we fly to Okeechobee Airport, like, it's been 45 minutes. We should be here now.
exactly. Yeah, like we were saying, celestial navigation is a way to update your position or get like an idea of your position, because it's not incredibly accurate. It's not as accurate.
Celestial navigation. I mean, it can be.
It can be, but with handheld tools,
All GPS is celestial navigation with celestial objects that are closer.
that is true.
And they kind of, and you don't have to measure them; they kind of measure for you. But
that is true.
It's the same thing.
Okay, we'll get to that. Okay. There's something I want to talk about
Okay.
At the end that's very cool that I saw online. But we'll go back to the beginning. So, at least in my opinion, my takeaway was that celestial navigation all boils down to is the measure of angles, right? Measuring the angles between celestial bodies and the horizon, or the angles between two celestial bodies. And it relies on the fact that we can, yes, we have the universe and everything is free floating and moving around in its own orbit. But from our perspective, we can consider the universe to be the Earth, the movable objects, the sun, the moon, the planets, and then a fixed sphere behind that doesn't move. It does move, but over the course of hundreds or thousands of years. So all of the methods rely on this assumption. Is that roughly true?
Yeah, they rely on the predictability of the celestial bodies, because like you can predict in the future let's say location between like Regulus and Polaris in the sky that's known for different locations around the world for the next infinity years. Yeah. If someone bothers to calculate it. So you put that in a book, use those angles, there you go.
But something like that is what I'm saying, like the distance between two far away things that are in that outer sphere is kind of assumed to be constant.
You're right, it wouldn't be Regulus. It would be Regulus in the moon.
That's right.
Yes, sorry, yeah.
So, the most basic, so I said the most basic thing is the measurement of angles between things, and they've had different ways of doing this over the years. Do you want to take over? I know you talked about like an ancient like way of measuring angles.
Oh, well, I mean, yeah, there's the astrolabe, which we'll just skip to the sextant real quick.
Okay, yeah, pull it up. We just picked up the sextant like 30 minutes ago, so we haven't used it.
And we totally know what we're doing with it. We're not going to break it. So this is a sextant. The astrolabe is essentially very similar to a sextant minus the lenses. It's like basically a tube attached to a compass, and you line up the tube with the object, and usually the sun, I guess sometimes Polaris, and then you lap the tube with the sun, and then you, with like a string hanging, you can see exactly approximately the altitude of the object in degrees. And that's kind of the very rudimentary way of doing it. And then the sextant refines that. I'm not sure.
There's also the octant. Well, let's hold off on that for 1 second. I want to talk about some earlier methods, because I misunderstood what the astrolabe is. The astrolabe is an ancestor of the sextant.
Yes.
So there's another tool. I can't remember what it's called, but I think it was from the Middle East, where it was a block of wood or bone, like a rectangle, with a string tied through the center, and there would be knots along the string. And so you would reach out and place this object so that it fits perfectly between the horizon and the object, right? You can do that by moving it in and out. And then you would measure how many knots it takes to get from the block to your mouth. And that was like a rough estimate of the angle between the object and the horizon.
I guess I don't know that's not an astrolabe, but I remember in Mr. Lovelace's Earth and Space class, he called them astrolabes.
You're probably right. I didn't go too in depth into the history.
But I guess those are doing the same thing, like, kind of the same way, I guess.
Yeah. It's effectively all of these tools, sextant, octant, astrolabe, whatever this thing is called, are just fancy protractors.
Yeah.
Right? You're just using it to measure the angles somehow. Like there's even the trick, if you've heard that, if you hold you probably heard this from Mr. Lovelace too. You hold your fist out at arm's length. Your fist takes up approximately 10 degrees. Is that right? 10 degrees of arc.
So that's just under an hour. 15 degrees is an hour. Well, 15 degrees of longitude is an hour. We'll get to that. But no.
Sorry, what? He goes,
how many degrees of longitude is an hour? 3.
It goes seconds, minutes, degrees.
Right. An hour in time.
Depends on how fast you're going.
No, like an hour in compared to Greenwich time, compared to your local time.
Of longitude?
It's 15 degrees per hour, right?
That sounds... So that would imply that 15 times 24 is 360 degrees?
Yes.
Let's see. This is good podcasting. So 24 times 15...
Technology.
All right, you do that while I think. Yeah. That's going to be 200...
Yes. Okay. I pushed him.
Yeah, okay. I see what you're saying.
That's unrelated to your fist, I believe. Well, yeah, definitely unrelated because your fist is kind of more measuring latitude if you're...
It just measures angles, nothing more. You can use it how you want to use it. So like, for example, we're here in Melbourne, Florida, where the latitude is, do you remember?
34?
28.
28.
34, I think, was North Georgia. So, and I remember that because if you go outside and you measure the horizon to the North Pole, or the North Star, we're giving away a little bit here, and you do this, it's just under 3 fists up to Polaris.
I should have known that because I have an equatorial mounted telescope and you have to put it exactly to... I just haven't used it in so long. I forget what it's set to.
Yeah, that's true. Well, so... obviously a fist is a very crude way of measuring an angle, especially because when you're actually trying to navigate, you need accuracy down to about the arc minute for effective, or maybe even like half of an arc minute. I think they said that 1 arc minute is effectively 1 nautical mile of error. So when you're sailing, they said like a good navigator could get it within 5 constantly. And like a great one could get it within like 1.5 constantly, which is pretty good.
Did you go into like how to split degrees in the minutes and seconds, and how that equates to nautical miles around the globe?
Little bit I talked about in the first episode. If you want to talk about that real quick.
It's like let's say we're at the equator. There's 360 degrees around the sphere of the Earth. Split that. Each degree gets split into 60 minutes. Each minute gets split in 60 seconds. And each minute is exactly 1 nautical mile at the equator.
I think that's the definition.
Okay. Yeah.
So it applies at the equator. It also applies for north-south travel along meridians.
Yeah.
So we had that device to measure the angle. Like the fist is the silliest one, right? And then we have that device with the ropes, with the knots. And then the astrolabe, which Hunter said is like a tube that you kind of use to like point at the star, point at the horizon, measure the distance. And then they had the octant, which is the direct ancestor of the sextant, which...
There's less lenses on it?
Less lenses. So this... We'll talk about all these parts later, but it effectively has 2 reflective surfaces here and here, so that when you look through it, you kind of see a double picture of the 2 objects you're trying to bring together.
They're split like this.
They're split, diagonally. Vertically. Yeah. And you try to on one side you see one, on one side you see the other, and try to bring them together. So an octant is very similar, just with 1 lens. So it's not quite as user friendly. One reflective surface. Sorry.
Got it. Okay.
How it exactly works, I don't know because I don't have one. There's not a lot of videos of how to use it. So yeah, we can talk a little bit about how the sextant works.
But go back to octant.
Yeah.
Octant means 8. Sextant means 6. Why is the octant the predecessor to the sextant? Someone explain to me that.
Why is this even called that? I don't know, because it goes from 0. It goes from -5 to 130 degrees. So it has nothing to do with a sixth of the circle. Yeah. Like I was thinking, maybe a sextant goes from 0 to 60, 1/6 of the full circle, but
why does that go to 130?
In case you want,
you wouldn't.
Actually, would that even work? I guess it would.
It goes to negative to check for errors. I know
that's
that,
right.
Like side error.
I don't know.
Okay.
I couldn't tell you. As we learn more about this, like I was saying, I just picked this up from a family friend who's a boat captain just before recording, so I didn't have a chance to play with it.
Shout out Captain J.
Shout out Captain J. So maybe I'll do a follow-up episode, the wingwag in the field, as you were saying.
Yeah.
Where Hunter can bring his telescope and I can bring the sextant. We can do some.
Don't know how much about airplanes that is, but yeah,
that's okay. So we can go through the details for how it works. Yeah, I think we'll skip like the exact details of how to use a sextant This one,
it just measures the angles and has a bunch of shades, so you don't get blind.
That's the important part. Yeah, these things are shades so you can look at the sun.
Yeah.
And how does this fit in here? Something like this. So once you have this angle, how do you use that to actually calculate your location? So the easiest thing to calculate is your latitude, and to do it during the day, right? This is the easiest sight. They call it taking sights, right? When you do a measurement with a sextant. So the easiest thing to do is to calculate your latitude during the day. Do you remember how to do this?
Is that taking a noon sight?
Taking your noon sight.
Yeah. But that's not, it's easy only if you have the required books for it, right? You take a noon sight, you can't.
I don't know if there's a way to do anything without books.
Well, you can get your approximate latitude by, if Polaris is visible right at dusk, Polaris isn't exactly north, but it's pretty close. You can sight Polaris, and I think it'll get you.
Okay, actually, that's a good point.
It'll get you in the vicinity.
Let's say that. Finding your latitude at night is easier.
Well, not at night, because you can't see the horizon at night, right before nighttime. Yeah.
You have to be able to see the North Star and the horizon.
Yeah.
So the good thing about the North Star is it's always almost right above the North Pole of Earth. And so if you can imagine, if you're standing on the North Pole, it'll be directly overhead. If you're standing on the equator, it'll be right there on the horizon. Yep. And so if you're between the equator and North Pole, it'll be somewhere in between. And it turns out that it just so happens that if you measure that angle between Polaris down to the horizon, Kiara, cut that. No, down to the horizon, that is approximately your latitude, right? Yeah. There are some corrections you could do, like based on the time of year and
the Polaris kind of circles are the North Pole. And in the South, if you're in the Southern Hemisphere, you're kind of screwed. They have the Southern Cross, which, again, I've never been in the Southern Hemisphere. You have. But I think you just kind of aim somewhere in the cross, and that is where the South Pole is, and you can do the same thing. But it's not as easy to find as Polaris.
Do you know how to... Actually, this is kind of a leading question, and there's many ways. But I found an interesting way to find Polaris. So there's a couple of things. You can follow the Big Dipper, or is it the Little Dipper? I think it's the Big Dipper. You follow the Big Dipper, and the tail points to this star. Or you can have a camera with high exposure, and you just leave it open all night, and the stars, as they move through the sky, or as the Earth rotates under them, will form arcs. And the star that is they're all circling is the North Star.
Again, this is a tangent.
Go.
I'm in the process of researching to buy what's called a star tracker, so I can mount my telescope or camera on the tracker, and it's equatorial, so you angle it exactly up to about Polaris, but to the north. I don't know what the actual word is for the celestial North Pole, I guess is what it'd be.
You're talking about if you put a skewer through Earth?
Yes. And so all the stars seem to spin about. It's around Polaris. So it's a mount, and then you angle your camera there, and then the mount tracks the Earth, so you can take tracks stars. It counteracts the movement of the Earth, so that you can take long exposure pictures.
So it moves your telescope for you?
Yes. So you can take long exposure pictures of nebula and galaxies, which are so dim that you need long exposure, but if you do a long exposure, it blurs because they're moving.
That's interesting.
They're super expensive because you need very accurate tracking, obviously. Yeah. So
we'll talk about this later, but maybe we should build one.
That would be really cool.
Yeah. So we'll get when we talk about modern celestial navigation, we'll talk a bit more about that because it is still in use today, even though a sextant is a very old tool. You might think that a sextant is completely obsolete. It is not. Most ships that travel the open ocean do have one in case of emergencies because it's not going to fail. I mean, unless you break it. But
this was on board our grandparents' boat.
Yeah, this one actually saw action and was used for navigation.
That boat had mini GPS, and they still had it just in case.
That's right, because they said celestial navigation can't be jammed, doesn't require any outside signals. Any human-generated outside signals.
Yeah, it requires a lot of outside signals. I mean, I guess...
And it doesn't require electricity to do some basic stuff.
Yeah. But I guess we're going back to what we were saying about taking the noon sight to find your latitude. At noon, you're gonna measure the angle of the sun. Then you have a book that will tell you latitude based on that angle.
That's right. So to get your latitude at night, we talked about Polaris. To get your latitude during the day, you wait until your local noon, which is key. It's different than actual noon because of the width of time zones and some other factors. Local noon will happen somewhere between
solar noon.
Yes, solar noon. When the sun's at its highest point, it's probably between 11:30 and 12:30.
And actually,
where you are,
solar noon gets adjusted a little bit due to the refraction of the sun coming in. But so the book does that for you, thankfully.
So what you do is you start taking readings as you think the sun is getting to its peak, and then you wait. So you keep taking your readings with the sextant until you find what actually was its highest point, and then you note the exact time, down to the second, that reading was taken at. And then let me pull out the book. So I got these books too. So this is the Nautical Almanac from 2023. So obviously it's out of date. It's 2026 right now. I believe this is the book where you look up the corrections, right?
Yeah, there's some, I believe. Yeah, these site reduction tables.
This is the one I saw on the YouTube channel. Oops.
These will also have these.
But these don't go out of date, he said.
No, this is for time of year.
So this one, I believe is this one, but maybe it's that. So anyways, you look up what time it was at and the date. You look it up in the book, and it tells you what the sun's current elevation, or its current, I think they call it declination, with the Earth is in that moment. And then you can either add it or subtract it from your reading, depending on which hemisphere you're in. And that will give you your latitude.
Yep.
Right.
That's pretty cool.
Yeah, it is cool. So obviously it does require this book. You have to have an updated version of some book at least. But again, it is nice because the book doesn't require electricity. Can't be jammed. Can't be EMP'd.
Yeah.
Maybe we'll get that out. It's kind of cool.
The creation of the book requires electricity, so you better have books well into the future.
So I was actually thinking about this. Yeah, in that case, we should get a very shielded hard drive where we load up these books for hundreds of years, just in case.
I bet the U.S. government has that.
I'm sure they do.
I know they're already it's kind of related. Really looking into non-GPS navigation, just in case. I'm sure they had to think of that.
We'll get back to that. Okay. When we get to the current and future of celestial navigation. So what a lot of old sailors would do, and I'm assuming old aviators, the early Atlantic crossers would do something similar, is they did not Great Circle route it, right? They did not go straight from point A to point B as efficiently as possible. They would go to a known latitude, or they'd go to the destination latitude, and then just try to stay on that latitude all the way across, right? So I might, we have a map right here. So if you're leaving from Spain, for example, you might follow the coast of Africa down until you get to the latitude of Florida, if that's where you're going, and then follow that across the ocean, trying to stay right on that latitude. And that way you don't even have to worry about longitude. If you're on the right latitude, you'll know that when you hit land, it's Florida. Right.
Yeah, that's pretty convenient for airplanes because they go fast enough that you can live. You can live when there was sailing. I guess longitude was a little more important because you need to know how far you were away because sometimes if the winds were right, you would be there for a long time.
That is true, but there are many expeditions that crossed large bodies of water using only latitude.
Yeah, you're talking boats or planes?
Boats.
Yeah, I'm saying, but I can understand why a sailor would really want it.
Yeah.
The way you describe with planes, I'm that seems pretty simple. I mean, it's not efficient, but it seems, just to take your readings, it's easy to find your latitude, and you can do a pretty
It's also less mental work.
Yeah.
So that brings up the thing we were just talking about, longitude. So latitude is a relatively easy thing to calculate. We just went through two methods, and we are not expert navigators by any means, and I feel like we have a decent grasp.
And importantly, those methods don't require you to know the time anywhere else on the Earth, which we'll get into with longitude, but
that is true.
So for those methods, all you need is just a book of predictions and something to measure the height of the sun, basically.
That's right.
Yeah.
And so the longitude is like the vertical lines on the Earth, right? So to know how far east or west you are at some point is a lot more difficult because it requires you to know the exact time at a particular location on Earth. In general, we would say Greenwich Mean Time or UTC. It requires you to know what kind of like the baseline of time is. And so you could, if you knew what the time was in Greenwich, you could effectively look at what your local noon was and say, okay, my local noon happened at 8 a.m. Greenwich East Time, according to this Greenwich Mean Time, according to this GMT watch. Therefore, I know that I'm wherever.
4 hours.
4 hours
way.
that way. Yeah, I'm inland. Yeah.
So
I guess it would be
4 hours is 60 degrees. If you're on the equator, that's how many miles?
60 degrees times 60,
3,600 miles.
3,600 miles.
If you're on the equator, you'd be Greenwich 3,600. You're in a rough area. No, I think it's more.
Yeah. So that's the idea, right? You compare what you're seeing with what time it is at some baseline location that you know the longitude of.
Mm-hmm.
In practice, GMT. So that sounds like a very simple problem because it's very easy for us to get GMT nowadays. Both of our watches right now have GMT readily available.
Even Rolex makes a GMT watch.
Even Rolex makes the GMT.
Yeah.
We wouldn't know about that. But back before then, like even knowing time was not a given, right?
Yeah.
When they had these
knowing solar time was always a given, but
knowing
solar
time,
knowing other times, I guess.
Yeah, knowing times other than noon, other than local noon.
Yeah.
So the first hurdle they had to cross was how to know what the time was in Greenwich, England on a ship. Because at the time, the best clocks were like grandfather style clocks, right? Pendulum clocks that relied on a swinging mass that swung at a very regular cadence.
Guess when those were invented? The pendulum clock.
Pendulum clock? 1500s?
I believe 17th century, so like late 1600s, which seems
really
late to me. That's kind of crazy.
So when we get to this, then that means that the life of the pendulum clock was actually not that long.
Grandma still has one,
but the life where that was the pinnacle of timekeeping. But the problem with the pendulum clock is when you bring it on a moving surface, like a ship. The pendulum is no longer swinging at a regular cadence, and so it would stop keeping time perfectly. Mm-hmm. And for these methods, you need to keep time perfectly. So before they had any other solution, some very ingenious navigators came up with some methods to calculate what the time was in Greenwich. And real quick, in the Dead Reckoning episode, I was talking about how, in my mind, navigators, up until possibly recently, have been at kind of the forefront of human ingenuity because navigation was such an important part of human civilization. They've kind of like really pressed technology for all it could do, technology and mathematics and science.
Yeah.
And so this is a perfect example. I have no clue how, but some astronomers determined that by measuring lunar distances or some factors about the moons of Jupiter, they could tell what time it was in Greenwich down to the second. Do you know about any of these methods?
Yeah, well, I mean, I know the idea of the method.
Okay.
The problem with, let's start with the moons of Jupiter,
mm-hmm.
jovial moons, right? There's 4 of them, and
it's way more than 4. 4 that are visible. Maybe. I actually don't know.
I don't know what yeah, I guess I don't know, like, are satellites around Earth a moon? No, I think it may be just 4 actual moons. Ganymede, Io, Europa, and Callisto. So those are 4 that we, like, you can see. You can't really see with your eye, though. That's a problem. So, like, theoretically, you can predict the location, because, like, basic astronomy physics. You can predict the location of each of the moons in relation to Jupiter for any time in the future. So if you have a table of all those locations, then if you can somehow measure those locations of the moons with respect to each other and Jupiter, you can kind of back into a time or location, anything that your book has. The problem is you can't really see them with your bare eye. I mean, maybe you can see them, but you can't really measure them. So you need a telescope, and that's not really feasible on a boat. So that never really worked out. And then, so similarly, there's a lunar, which is, correct me if I'm wrong, is that when you're measuring the distance between certain stars and the moon? And then
That's right.
that's in a book because that's also predictable.
Yeah.
And then you can back into anytime you want, usually Greenwich Mean Time.
That the lunar distances, I think, makes a lot more sense to me, at least when I imagine navigation. I know this is not right, but when I imagine navigation as Earth-centric with the moving shell and then the constant shell of stars beyond it, we know that independent of the rotation of the Earth, the shell that contains the moving moon is like clockwork. We know exactly where it should line up against the non-moving star shell. And so if we can measure the distance from the moon to a couple of different stars in that non-moving shell, we know exactly where it currently is sitting in space. And we can just look at a book and say, okay, because it's clockwork, we know that it's supposed to be sitting in that place at exactly 11:23 and 58 seconds in Greenwich, England. And so, okay, well, that's where it is now. So it must be 11:58:23 in Greenwich, England. And now I have the time, and I can use that for future longitude calculations.
Yeah, and that method is almost more appealing to me because
I love that method.
Yeah, we live in like the natural clock. We're in the middle of or not in the middle, but we're part of the clock with the the Earth going around the sun, the moon going around the Earth. Like we should use that because it's always going to be right because our time is based on that.
Yeah.
But yeah, like everything I read says the lunar method. It never caught on because it was too complicated. I'm like, doesn't sound that complicated. It seems maybe it's complicated to make the figures in the books, but who cares? The sailors aren't making that. But I guess it just comes down to taking the measurements at sea. Because I guess it's hard enough measuring just from the horizon straight up. And it's very important to hold your sextant perfectly vertical. And I guess when you're measuring stars that they're not straight up, but they're all goofy angles, I guess it gets tricky.
Yeah. Yeah, I heard it's a lot of work. Like on a flat surface, you might be spending 15 or 20 minutes taking measurements for the lunar distance. So I can see it. But like you said, it has an appeal a very natural appeal to this method.
When I first heard about the jovial or Galilean moon thing, it's like, that sounds sick.
Yeah.
But I don't think anyone ever did that on a ship. It's impossible.
It was just a theory.
Yeah.
Something interesting about like these charts. So obviously these charts are now populated via computer. So, like there's computer programs that are running and constantly keeping track of celestial objects, now man-made as well as non-man-made. But I remember reading that Euler, I think it was Euler, the mathematician, at one point he received a grant from some government of the world to just fill out one of these books. Like they paid him to like by hand do all these like lunar and solar calculations.
Do you think he did those or he had some assistance? He was sitting there just going,
maybe some assistance. Yeah. But I don't know for sure.
When was Euler or Euler?
1700s.
Wow.
Ish.
Okay.
I think. But like Hunter was saying, these methods are cool, but very frequently not doable in practice. Or they didn't want me to.
Bad weather, you can't do any of it. In an airplane, I mean, you're in bad weather a lot more frequently than a boat, so that's even,
So
maybe not more frequently. I take that back, but
then the vast majority of the mind power and money at the time that was going towards navigation methods started going towards just building a clock that could keep accurate GMT time at sea for the duration of a general ocean crossing voyage. So it had to be accurate to within, I think they said 1 or 2 seconds for 3 or 4 months. Like that was the certification. And I believe there was a competition. Do you want to talk about this? I know you read
first of all, audience, you should definitely read the book Longitude by Dava
Sobel.
Yeah, Dava Sobel.
Very
she writes a
good
lot
book.
of good science books, but they're not like textbooks or stories. And it's a story of John Harrison.
I believe it was John Harrison.
John Harrison was just a lowly British clockmaker and carpenter who wasn't really a scientist, wasn't a crazy inventor, and he developed the first chronograph, the first clock that could keep accurate time at sea. Because at the time, the English Admiralty offered the reward, or was that like the
Might have been
the Royal
the Royal
Astronomy-
Science Foundation,
Yeah.
or something like this.
some like government organization in England had a big monetary reward for solving the longitude problem, and it was like I think it was a tiered reward too. Like if it was accurate within 1 minute, you get this much money. If it's accurate within 5 minutes, you get a little less. It's really cool. And he ended up winning the reward, and it's in the book, The Longitude, because he developed, I think it's called HM1, which was the first chronograph that kept accurate time at sea.
It's also cut for all the Pokemon fans out there.
Okay.
That might get cut. All right.
I'm still waiting to get cut in Fire Red. Fun fact. I have 3 badges, still don't have it. Okay.
All right, continue.
Yeah, so the book, John Harrison, he kind of had a competition with there's a big scientist who is like a big advocate of lunars. Like to the point of, I think, kind of smearing John Harrison, like, this moron can't build clocks. He's an idiot. And let me find the scientist's name.
Sure, yeah.
A royal astronomer, Neville Maskelyne. I don't know. He was like actively trying to undermine John Harrison because he believed in the astronomical solution so wholeheartedly, which is kind of respect that. But a lowly clockmaker and carpenter ended up beating him out, which is pretty cool.
So there is, like we said, there is a natural like coolness about the astronomy method, but in my opinion, using a clock is also naturally cool because it has no outside sources. It's completely self-contained. And if I remember correctly, his series of clocks, like he released several, each more accurate than the last. They used the winding method of what mechanical clocks nowadays use, where you have like a mainspring that's wound, and that is the energy is released via an escapement.
Yeah.
But it's also a lot more resilient to movement. Like you can wear a mechanical watch and your arms like moving all over the place.
His clocks were not the most resilient in today's to today's standards for temperature and pressure. I was reading. They weren't great. Because I think they were mostly made of brass, which does expand and contract a decent amount with temperature. But it was like a HM1 was like a puck, like a brass puck, and it was, I think, filled with oil, and the whole thing sat inside this like puck of oil, and that was all brass, metal gears.
Maybe this wasn't HM1, but I also heard something like it would be stored in a box with gimbals, and then that box would be placed in the ship's hold, like down below, so that it would not receive any sun. It would be kept relatively cool, and would be as far from like the salt as possible.
And I think that boats at the time, if they could get their hands on, would typically carry 3, because
or more.
If you have 1, you don't know if it's accurate. If you have 2, you don't know which one's accurate. So if you have 3, then that gives you a little bit of backup.
I remember reading. I don't remember. It was a famous ship, but they always kept 22 on board. Because they were saying that it was the most critical piece of equipment on the boat. They could not risk.
That's crazy. Because I assume when they were when the chronograph was very first invented, which was 18th century, 19th century,
late 1700s, so late 18th century.
Okay.
But it wasn't adopted fully until like mid 1800s.
Yeah. So when it first came out, that's must be equivalent to, I don't know, rocket boosters today. That's the most cutting edge of science. And these boats, they had to buy them.
And they were probably spending multiples of the average person's yearly salary on one.
Yeah, I remember. I thought I read maybe 10 years after HM1 was invented, a good sea chronograph would go for 150 guineas. I have no idea what that is.
150 guineas.
I think that's what I read. Maybe it's 15 guineas, but something like that.
Maybe.
I don't know what a guinea is, or I don't know if that's a lot, but they made it seem like that's a big deal.
Yeah.
So.
Yeah, and I could be wrong, but I believe that to this day, military vessels still have an official ship's chronometer. That's that same style, like a box you open with a puck clock in it, and there would be someone on board. I don't know if it's probably not a dedicated job anymore, but I think someone still does it. Somebody goes, checks it against the other clocks on board, like the GPS clocks, the radio clocks, to verify that everything is in agreement, and then reports that to the captain every morning. Yeah,
the boat where this section came from, they had their fancy marine chronometer mounted right up on the bulkhead of the boat.
Yeah,
and it was there with the pressure reader. What's that called?
The barometer.
Barometer. Yeah, yeah, pretty cool.
Yeah. So, let's see. So we're talking about longitude. So now we have the accurate clock that can cross the ocean. Like I said, invented late 1700s, became like financially feasible mid 1800s. So at this point, they kind of stopped using astronomy really. They still use noon sights, but celestial navigation played less of a role in the calculation of longitude. You just have to do your one noon sight.
Yeah.
To see roughly like how far you had gone east to west. And then from that moment, celestial navigation that was the state of navigation for a long time, up until the invention of radio navigation. Probably that would be like World War II-ish time, which came with the advancement in aviation, because all these methods we're talking about work in an airplane, but airplanes are moving a lot faster and they're a lot bumpier than boats in some situations, so they're a little bit harder to do. And so new methods of navigation were needed that we'll talk about in future episodes.
But in World War II, they did use those good old-fashioned celestial navigation because, I mean, like, American planes were flying places where America didn't have bases yet that were sending out radio they could pick up. So
that's true.
They still had to do it then. And then I guess, the average GPS really killed it for airplanes. But
it did. So maybe this is a good time to talk about how it's still used. Like post World War II, what is the state of celestial navigation?
Yeah.
The coolest application that I saw. Did you see this? The navigation system on the SR-71?
No.
So the SR-71, if you don't know that plane, look it up. Very cool, very fast. I believe it was developed in the 50s and then became active in the 60s through the 90s. So pre-GPS through early GPS. And it's flying at Mach 3. And it's doing like secret reconnaissance missions. It needed to have really good navigation. So they built a custom, they called it a star tracker. That was like a camera mounted on the roof of the plane behind the pilot that at all times would keep tabs on the 11 brightest stars it could see and measure the distances between them and compare that to an internal database, which is effectively these books, but just stored in a computer, and use that to calculate its location.
That is very futuristic because...
Very futuristic. I want one.
Yeah, because that's like some of my star trackers or telescopes, like a way you can make it a little better is you have a little secondary camera that takes pictures of the sky you're seeing and then compares that to a database and makes tiny little adjustments to even make it more accurate. Like you sent me the article about the thing with the Raspberry Pi, like basically using a Raspberry Pi and a little camera to figure your location wherever you are in the world just by taking pictures of the sky and comparing it to a database.
Which I want to build. I think it'd be a very fun project.
That's kind of cutting edge now, I would say. That's crazy for the 50s and 60s.
What's wild, so this computer was probably developed in the 50s. And so at the beginning of the century, this and a clock were the pinnacle of navigation. And suddenly 50 years later, they have a computer that's taking pictures of space, and telling your location, which is...
I would love to see how that worked, knowing the computer power that we had, or they had in the 50s and 60s. How? Is it just... I would have to know, because that'd be handling a ton of data first we taking all those pictures. And also, how is it comparing to a database that it has on board of the locations? That seems... So I guess it's probably taking the picture, taking the angle measurements, getting rid of the picture. It doesn't really need that. And so it's just storing a few little numbers and comparing those to a database and just numbers.
So the way I understand it is with this kind of navigation, the star tracker method, you're only using the fixed sphere of stars. You're not using movable objects like sun, moon, and planets. And so you measure you measure and store just the distance. So if you're looking at 11 stars, you calculate the 11 choose 2 different distances that there are, and then the table stored in the database is just a list of distances between stars, and then you can I must be looking at these stars, and then you have an onboard timer or an onboard clock, which is a lot more accurate at this point. Compare that. At this point in time, I'm looking at this patch of sky, therefore I must be here.
Got it, because the actual distance between the stars shouldn't change.
So it's
more like position of But don't the stars have? Don't you need to be looking at the stars in relation to something that has to do with time in order to?
I don't think so. I think it can be as simple as this. You know exactly what time it is at your location, and you have to be looking directly up or at a known angle. I think that's the key. So you said so you look up and let's say you see the Polaris directly at 90 at this moment. Where must you be? The North Pole.
Yeah, that makes sense. And I guess having time already is the key point there. Yes.
So in the star tracker that I want to build with the Raspberry Pi, I think it would be cool if we add a radio receiver to receive the atomic clock radio signals, but then also add the ability to have it do lunars for you to update, like in case you lose that radio signal.
That would be really cool.
Yeah, and it'd be fun to try to like program it, you know.
Yeah.
So yeah, like we're talking about databases. So they still do publish these books. This says 2023, but these are strictly backups nowadays for in case the power goes out. In reality, they use computers, or like the sextant came with this TI-89, which came loaded. It came loaded with a star tracking program. So you just enter the readings that you see off of the sextant, and then what you're doing, like a noon sight, for example. And then it does the calculations for you and spits out your latitude and longitude. And so that's effectively what a star tracker does, just internal.
Yeah.
And I don't know exactly if that same system from the SR-71 is still in use or if there is an equivalent in the military. I do know that a lot of active military airplanes do have a sextant hatch. I believe the B-52 does, and I think C-130s do as well. Because at work, my company does internet for airplanes, and they sell an antenna. And I believe they sell an antenna to the military that fits in the sextant hatch of a certain airplane, which is kind of funny that either a sextant goes there or a satellite internet antenna.
I do wonder if they are putting a sextant to the sextant hatch, or I mean, if they ever use it, but if they're putting a small star tracker.
That's what I'm guessing it really is, a small star tracker.
Yeah, I mean, I think your iPhone could probably do it. Yeah, just there you go. Yeah.
So So celestial navigation is still alive and well. GPS is better. All the ground-based methods are better. But we talked about the GPS spoofing episode a while back, that GPS is very degraded and sometimes just flat out wrong in many areas of the world. And it seems to be expanding. Like it was just the Middle East for a while. Now it's the Russia and Ukraine, the Mediterranean.
You're talking about when it's intentionally kind of messed up?
Yes, it's when it's intentionally messed up. And it's spreading into Europe. And I think a lot of people are rightfully concerned about this. So I remember reading that maybe it was the Navy stopped doing celestial navigation in the 90s, but then they brought it back in like 2015, 2016 for this reason. And a lot of military branches like the Coast Guard never even got rid of celestial navigation and are pushing it more now. Good. Because it's the only one that can't be jammed, right?
Yeah.
But except for biclouds.
Yeah, it does get jammed a lot, actually, especially in Florida.
I have no evidence for this. I was not able to find anything online about it, but our brother Matthew, he claims that military airplanes carrying a nuclear bomb are required to do multiple forms of navigation simultaneously, and that one of them needs to be celestial. And I do believe it. Like, no evidence, but I do believe it just because it's kind of like the ground truth to compare to the other ones, right?
Yeah,
like you can't fake it.
Yeah, I would have to guess though that in today's day and age in our military, the source of truth is still GPS. Like they're probably comparing their celestial their celestial waypoints or locations they're calculating with GPS. And then if it's different, they're not going, oh, GPS jam. No, they're going, oh, we took a bad measurement.
Probably.
So yeah, I guess it's just if GPS signal just drops out completely or it's clearly wrong. But
And as Hunter said at the very beginning of the episode, it's kind of a misnomer. GPS is technically celestial navigation, right?
Right. So I mean, this is
they're man-made.
Yeah, break it down simply. Like if you have a sphere and you have a point up here, and you measure the angle of that's like, so the measurement angle from Earth to that point up in space, it's the same angle around the circle on the sphere. So if you just take one measurement, one angle, you're somewhere along this circle. And you pick another one, you're on another circle, and you have 2 points. And like GPS the same way, so ultimately you need...
There are benefits to GPS, like effectively the signal that we receive from the star is its light, which encodes no information about its location. Whereas the signal we receive from the satellite is the GPS signal, and it does encode information about its location. So we do get like a computer doing traditional celestial navigation versus a computer doing GPS navigation. The same computer will get a much more accurate reading with GPS for that reason. Like even a computer doing celestial navigation does not get to the like meter precision we see from GPS.
I would have to believe it could, though.
Maybe it could.
Yeah, I think if you do enough and come up with the right correction to use, given like how far the light's traveling and the kind of bending is happening, I think you probably could get just as accurate.
Maybe. Well, there's something we'll talk about in a second that kind of blew my mind, but and then so we're talking about celestial navigation, definitely still in use, and it will continue to be in use for a long time, especially because as we get into more space travel, celestial navigation is the best way to navigate in space. You don't have any landmarks. It doesn't even make sense to talk about landmarks because you're not on a planet. The only thing you can really do is dead reckon with celestial navigation, right?
Right, and like assuming humans go interstellar, we're going to be in places where we don't know the star locations from that point. So then all you have is dead reckoning, right? Yes,
but I imagine that our current perspective of having the shell of fixed stars is no longer, that model is no longer going to work. We will instead have to store like a 3D picture of the universe with all the stars in their 3D locations with reference to some center.
Currently we can't do that because right
we
now
know it for some stars.
We're getting but they're big estimations that may cause problems. Like
they do.
Thousands of light years estimations here.
So there are some objects in near area, the galaxy,
like Betelgeuse, like we know basically where that is, I guess. Yeah.
And there's a couple like pulsars in particular. We have a really good way of knowing how far away they are. I don't know how. And did you read about XNav at all?
No.
I don't remember what it stands for.
Okay.
Actually, maybe I do. But it's still in development now. It's called X-ray. I think it's called X-ray pulsar navigation. It's effectively GPS, but instead of using satellites, it uses pulsars. And I think we do have a method of knowing how far away they are. I'm way out of line here, but we know every pulsar has a unique signature. It has a frequency. It's a spinning star. It's a neutron star that's spinning very fast, and that spin causes electromagnetic radiation to like be ejected from the poles. And so if that spin is in a certain reference to Earth, we can pick up those like lighthouse lights every time it spins. And so measuring the frequency of the spin and then something about like the phase of the light, the frequency of the light, I guess, that gives a unique signature to the pulsar. And then we can somehow estimate what its real size is and then use that to know its real distance. And then so the XNav system is basically you are going along, you're measuring the phase of the light and the frequency of the pulsar from a couple of pulsars that you can pick up. And then from that, triangulating from their known locations to figure out yours. And in a test, I read that they got the accuracy to 5 nautical miles. Which is crazy.
That's very crazy.
In one way, it's crazy high, and in one way, it's crazy low. Like when I think about, like, wow, they just use stars so far away to calculate
millions of light years.
But then I'm thinking, like, you have a computer measuring things perfectly, and you got 5 miles.
I guess thousands of light years. That's still, that's...
Yeah. I think that was just like a preliminary test, and it's like no airplanes are actually using this. No spacecraft are using it yet.
5 miles in space, that's probably enough.
That's basically right there.
Yeah.
and they were saying that, like, I don't know the details here, but the unit to receive X-rays is a lot smaller and lighter weight than a traditional like celestial navigation system. So it could possibly fit onto a lot smaller stuff. And I think something like this could be used for aircraft or spacecraft.
That's cool.
Yeah.
We have to get one for our plane when they come out.
Oh, for sure. Oh, we'll make one. We'll make another Raspberry Pi one.
I guess GPS should come first. But
Yeah.
one of those.
Well, I was telling Matthew, you know what I want to do? I want to make a star tracker with a Raspberry Pi, like we were talking about, and have it like do lunars and stuff. I want to make a couple copies and like give it to like the important people in my life so we can all find each other in the case of something bad happening.
That's pretty cool, yeah.
And it's solar powered.
Okay. Need that. And EMP proof somehow.
And EMP proof is shielded.
Yeah.
But if not, we'll just pull out the old sextant in the books and make sure I have this year's book.
So yeah, me and all my best buds know where we're at, but we can't communicate it to each other.
Well, we'd have to say ahead of time. Hey, let's meet at.
Somewhere out there, Jack is also finding his Latin law.
We'll say, Hunter, let's meet at what used to be Witt's Ice Cream. Yeah. Yep. Anything else that we should talk about?
Charles Lindbergh's crossing the ocean.
How did he do it?
With an airplane. No,
Swam it?
I think he was mostly just dead reckoned the whole way.
Really?
Yeah, using the or I'm not sure if it had that then, but something of that nature. The inertia.
Yeah. Also a compass, which I don't know if that counts. Does using a compass count?
As dead reckoning?
Yeah.
Yeah, you need a compass because you need at what speed you went in what direction.
Okay.
So you need a compass. But yeah, and I think that's because I remember reading that his wife flew with him a lot of times, if not all the time, and she was his navigator. Because I guess he thought navigating was for women. Flying planes is a man's job or something like that. Mm-hmm. So she would, but then also, because there was a special watch that some watch company still sells. It's called the Lindbergh. Oh. And it's like so just like, it tells time, but then like the bezel moves in a way that makes it easy to calculate Greenwich Mean Time given your observation using sextant.
That's cool.
Yes, it's really cool. It's all mechanical. I was like, I would love to have one of those. It's kind of a brick though. It's a big boy, but it's cool.
Should we look into getting boys Lindbergh watches?
That would be fire.
Yeah, I'll see. Maybe if 2026 treats us well.
Yeah, if you get enough podcast viewers, listeners.
Yeah. Oh, the Sunstone was kind of interesting.
Yeah.
I read about this. I don't know if it's actually proven to even be true, but in a couple of like some of the old Viking boats, they found a clear crystal. It was a certain element. I don't remember what it is off the top of my head. And the leading theory is that they would use this to find the sun when it was overcast. And the way it works is that this crystal is able to somehow detect like the polarization of light, and the light coming from the sun is polarized in a certain way. And by like holding this up to the clouds and like moving it back and forth, you can like notice like some image, I don't know, appear on this stone that tells you like where the sun is. And then once you have that, you can use like another angle measuring method. They probably didn't have like something as sophisticated as like an astrolabe. They probably had something more like the bone with the rope attached. But they could get like a rough estimate of their latitude.
That's cool. Don't know if it's real, but
don't know if it's real either, but it is cool.
If it works.
I should get one. And just put it in the box of the sextant.
Also, go back to the SR-71 navigation.
Yeah.
How are they seeing the stars flying at daytime? Like, does it fly high enough to see stars?
No, you can. I looked into this.
Like high exposure?
They have certain filters you can buy for cameras that allow you to see stars during the day.
So filter
because
the sun
they
out.
sell one that fits on this certain Raspberry Pi camera.
Okay, so you can do it during the day.
So you can do it during the day, which is really cool.
That is cool.
Yeah, I didn't know that either, that it was possible. But yeah.
Well, another Davis Sobel book. So read Longitude, and then she wrote a book called Copernicus. No, maybe it's not called Copernicus.
A More Perfect
Heaven. A More Perfect Heaven, something like that. Yeah, but it's about Copernicus. Great read, and all this is possible because Copernicus. He was the one who obviously invented the heliocentric, he thought universe, but in actuality solar system. Very cool, good read. So I
need to read that one.
All this is kind of based on his work, and he was really almost literally crucified for it at the time, because he was a Catholic bishop himself, and they didn't love what he was saying. So, yeah, cool dude.
Yeah, and here I am over here
Good work.
talking about the theory of spheres, which was like...
No, it's honestly unbelievable how close Copernicus got to the truth that we understand now of the celestial bodies 400 years ago, when he didn't have a telescope. Yeah, so without a telescope, he came up with all these and was pretty much correct. So
how did he do it? Just thinking? Or was he doing some sort of measurement?
So at the time, it was super like astronomers were also astrologists. That's how they made a living. Like a king would hire them, and they would like predict like if Mercury would be in retrograde, and it was important if like their daughter would be born hot or not. I don't know. So that's
yeah, I remember reading that.
And I think that like astronomers knew that it was kind of bullshit, but they needed to make money. So that was what they did. And there was a big deal about predicting the movements of the planets, because if you could predict them right, you could tell people, oh, Mercury's going to be there in a month, and when it's there, you're a magician. And there was some problems with so they would try to model the movement, and every time they tried to model them, they would I guess naturally they go the heavenly spheres movement of Mercury's in a sphere that's around our sphere. It's like a separate shell and it moves. But then the retrograde motion of some planets, and some planets appear to be faster than others at some point, that always threw off these models. And then at the time, people's they would come up with these wild explanations that they weren't real explanations. That's just how it is, basically.
Yeah, the sphere would actually just reverse for a little bit and then continue.
Yeah, it was kind of ridiculousness. And then, I guess Copernicus kind of gathered all those inconsistencies, just thought, how could I make that make sense?
Sure.
And then he just backed into that the sun was the middle of the solar system, everything is orbiting the sun, the moon's that whole thing. So, yeah, very fascinating.
What I'm really curious about, maybe the book talks about this, is did he actually discover this? Or was it such an unpopular opinion, but lots of people thought it, but no one wanted to say it out loud, and he was the first one to say it out loud? Because it seems obvious now.
He did not discover it. He proved it. Or not proved it. He proved it through...
previous observations?
Through prediction.
Okay.
He predicted the movement so perfect, that's basically proving it.
Whose idea was it? Is it old, ancient?
Yes. I think Ptolemy at some point hinted towards a heliocentric solar system. He thought universe, but he was really inaccurate, and he didn't get the things about Copernicus got how planets orbit correctly. He didn't get quite to elliptical orbits, but he got different. It was very impressive.
Pretty good.
Very good. That's not really related to navigation. Well, it is related to navigation, but maybe not. Maybe not the scope of this podcast. Maybe we'll have to come back and do an astronomy podcast.
Yeah. Yeah, if this ever turns into the Wingwag Aviation and Astronomy podcast, I think that's okay.
That'd be awesome.
Yeah. Though, after doing all this research, there was one day when I was sitting there watching YouTube videos of the Practical Navigator, a guy who has a sailboat in the Caribbean, and he just teaches you how to use a sextant. I was like, cool. Should the Wingwag be an aviation and also a boat podcast?
Yeah.
Why not?
Next episode, we'll get out on a boat.
Yeah. But like I said at the beginning, I definitely want to learn how to use this and get good at all of this stuff, and maybe do a recording of us actually taking some readings.
Yeah, fortunately we live by the beach, so we should be able to find the horizon there if the waves are flat enough, I guess. Yeah.
Let's see. Last thing, you want to put the Concorde back in its landing configuration for me, please, Hunter?
Kansas podcast at full speed.
All right, I think that's it.
All right, cool.
Thanks for coming in.
You're welcome.
Thank you for listening to The Wingwag. If you liked this episode, please consider subscribing. And if you're out flying today, make sure to give somebody a wingwag.